systematic way to tackle problems in mechanics. Draw a free body diagram. Choose convenient coordinate system. Consider all the forces acting on the body. Resolve the forces in the chosen coordinate system. Apply Newton's laws of motion and solve all the equations to find the unknown variables. Let's take a look at each of the steps involved. To draw a free body diagram, we need to draw a schematic diagram showing all the bodies in an environment along with their links and supports. Then, we consider a convenient part of this diagram, relevant to the problem at hand, as a system. Then, we draw a detailed diagram of this system along with the external forces acting on it. This diagram is known as a free body diagram. This completes step 1 of the solution. In a free body diagram, we do not consider the forces applied by the system on the environment. Next, we choose a convenient coordinate system to resolve the forces involved. Coordinates should be chosen keeping in mind the probable direction of motion of the body. This makes the solution easier. Then, we add details about all the known and given forces on the system, indicating their respective magnitude and direction. Then we resolve all these forces along the chosen coordinate system. Finally, we can take the help of Newton's laws of motion to determine the magnitude and direction of unknown forces. If the problem at hand requires an analysis of multiple systems in an environment, we follow the same procedure for each individual system. To understand these steps, let us take a problem and solve it systematically. Bodies A and B of mass 10 kilograms and 30 kilograms respectively are connected by a rope of negligible mass passing over a frictionless pulley. The coefficient of friction between the masses and the inclined planes is 0.30. Determine acceleration of the system. Tension in the rope. Velocity of the system at the end of 4 seconds starting from rest. First, we draw the free body diagram. Here, as the two bodies are connected by a rope, we split the problem into 2 parts and tackle them independently. As the mass of B is greater than the mass of A, and the inclination of the plane on which B is resting is greater than the inclination of the plane on which A is resting, B is likely to go down and A is likely to go up the plane. Next, we choose a convenient coordinate system, XY, such that X is parallel to the inclined plane and Y is perpendicular to it. We choose X parallel to the plane, as body A is likely to move along the plane. This will make the application of Newton's laws of motion easier. Then, we denote the forces on body A, which are its weight, mg, or 98.1 newtons, and tension in the rope, T, which is unknown. Next, we resolve the weight of body A along x and y coordinates. The x component is equal to mg sine theta, which is equal to 49.05 newtons. Similarly, the y component is equal to mg cos theta, which is equal to 84.96 newtons. As there is no motion of A in the y direction, we can say the net force along y direction is 0. Summing up the forces acting along y direction and solving this net force equation, we get the normal reaction N as 84.96 newtons. Let us call this equation 1. As A is moving up the plane, the frictional force F acts downward. F is equal to the product of the coefficient of friction, mu, and normal reaction N. Substituting the value of N from equation 1, we get the frictional force F as 25.49 newtons. Let this be equation 2. As A is moving up the plane, we take the inclined plane's upward direction as positive. Using Newton's second law of motion, the net force along x direction is the product of the mass of the body A and its acceleration. Substituting values and solving, we get equation 3 as T minus 74.54 is equal to 10 times the acceleration of body A. Now consider the other part, that is, body B, and draw a free body diagram indicating the forces and a convenient coordinate system. The weight of the body B acts vertically downwards. This force can be resolved into its x and y components as mg cos theta and mg sin theta. Mg cos theta is equal to 147.15 newtons and mg sin theta is equal to 254.87 newtons. As there is no motion of B in the y direction, we can say the net force along y direction is 0. Summing up the forces along y direction and solving, we get the normal reaction N as 147.15 Newton. Let's call this equation 4. As the body B is moving down the plane, the frictional force F acts upward. F is equal to the product of the coefficient of friction, mu, and normal reaction N. Substituting the value of N from equation 4, we get the frictional force F as 44.15 newtons. As the body B is moving down the plane, we take the inclined plane's downward direction as positive. Applying Newton's second law of motion, the net force along x direction is the product of the mass of the body B and its acceleration. Substituting values and solving, we get equation 5 as 210.65 minus t is equal to 30 times the acceleration of B. Since A and B are connected to each other with a rope, the magnitude of their acceleration is equal. Substituting equation 6 in equations 3 and 5, we get T minus 74.54 equals 10A as equation 7. And 210.65 minus t equals 30A as equation 8. Equations 7 and 8 are simultaneous equations with two unknowns, which are t and a. Adding these equations and solving, we get acceleration as 3.4 meters per second squared. Substituting the value of A in equation 7 and simplifying, we get the tension in the rope T as 108.54 newtons. Now, we need to find the velocity at the end of 4 seconds. Given that the initial velocity of the system, v0, is equal to 0, acceleration of the system, A, is 3.4 meters per second squared, and time t is 4 seconds. We can use the equation of motion. V is equal to v0 plus at to determine the velocity at the end of 4 seconds. Substituting the values and simplifying, we get the final velocity, v, as 13.6 meters per second. Another way to solve this problem is that we can combine the two bodies A and B along with the rope into a system. Tensions T acting on body A and B now become internal forces and hence cancel out each other and will not be taken into consideration while writing the net force equation. The net force of the system along x direction is equal to the product of the total mass of the system and its acceleration. Substituting the values and solving, we get the acceleration A as 3.4 meters per second squared. The disadvantage of this method is that the tension in the rope T cannot be found directly. To find T, we have to write the net force equation for A or B, where we substitute the value of acceleration just obtained. That is, 3.4 meters per second squared. Let's consider the net force on body A along x direction, which is equal to the product of the mass of body A and its acceleration. Substituting the values and solving, we get the tension in the rope T as 108.54 newtons.